Welcome to the AI Research Roundup. I'm Alex. Today we are looking at this paper from the Hugging Face trending list, published on December 16, 2025, which was about 2 days ago. It introduces the Universal Reasoning Model, a streamlined universal transformer variant that hits 53.8% pass at 1 on ARC-AGI 1 and 16.0% pass at 1 on ARC-AGI 2 by leaning into recurrence, strong nonlinearity, short convolution, and truncated backpropagation. The paper is titled Universal Reasoning Model. Okay, and as we will see later, the interesting part is how much of the gain comes from simple iterative refinement rather than fancy architecture. Also, the authors shared a GitHub repo for Universal Reasoning Model. You will find the training and evaluation code, configs, and model components, plus dataset builders for ARC-AGI 1 and 2, and Sudoku. The README walks through installing requirements, prepping data from the included Kaggle bundle, and running scripts to reproduce reported scores. Figure 1 makes the headline point that the Universal Reasoning Model beats other small universal transformer-style baselines across multiple reasoning benchmarks. Pass at 1 means the model only gets one try per problem, so the score reflects first-shot correctness. In the left panel for ARC-AGI 1, the Universal Reasoning Model reaches 53.8%. The middle panel for ARC-AGI 2 shows 16.0%, and the right panel shows 77.6% on Sudoku. Figure 2 explains why the Universal Reasoning Model stays simple, but still reasons deeply, because it repeats the same block in loops instead of stacking many unique layers. This figure shows the full diagram, with a standard transformer on the left and the loop-based Universal Reasoning Model in the center. The center panel also highlights truncated backpropagation through loops, which means training only sends learning signals through later iterations to reduce instability. The right panel zooms into conv-swiglu, where a short depthwise convolution adds local token mixing inside the gated MLP. Table 1 nails down the practical payoff of the design choices, because it compares the Universal Reasoning Model against RM and TRM across 3 tasks. Pass at n means the model gets n sampled attempts, and it counts as a win if any attempt is correct. In the ARC-AGI 1 block, the Universal Reasoning Model leads at pass at 1. In the ARC-AGI 2 block, the Universal Reasoning Model also leads, and in the Sudoku column it posts the top accuracy. The ablations show that removing short convolution or truncated backpropagation drops ARC-AGI 1 scores, so both components matter. This table shows that looping a universal transformer can beat simply scaling a vanilla transformer, even when the compute budget is similar. Table 2 compares pass at n on ARC-AGI 1 across depth, hidden size, parameters, and flops. The vanilla transformer block climbs slowly and even hits a pass at 1 of 0 at one large setting. The universal transformer rows jump to a pass at 1 of 40, which supports the idea that iterative refinement drives efficiency. Table 3 shows that truncating gradients through the loop can actually improve reasoning accuracy, because it stabilizes training while keeping enough multi-step refinement. Truncated backpropagation through loops means the first few inner loop steps run forward only, with no learning signal flowing through them. The best setting uses 6 loops with gradients and 2 loops without gradients, which lifts pass at 1. Longer truncation hurts, because the model stops coordinating across iterations. Table 4 shows that strong nonlinearity is a make-or-break ingredient for ARC-AGI performance. The table lists ablations, which means the authors remove one component at a time to see what really drives accuracy. The full Universal Reasoning Model scores about 54 pass at 1, but removing the short convolution drops that to about 45. Replacing swiglu with simpler activations pushes pass at 1 down to about 29, and removing attention softmax collapses it to about 2. Alright, 2 takeaways stand out. The big gains come from recurrence, meaning the model reuses the same block to iteratively refine its answer, and from strong nonlinear MLPs, with short convolution as a small but meaningful boost. More broadly, the results argue that simple, loop-based compute can beat bigger stacks of layers for reasoning. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.